I was saying you can rotate this or make a random plane many times, and you're not expecting D to be contained on that plane. So what we're going to say about 4 points of information is we're going to say 4 points are overspecified. There is no way, sorry, it's not, it's overspecified. There's no consistent way to make a plane out of 4 points. Unless as 2 of the points are collinear. Then you're really talking about just a 3-point situation again. So you can make a plane, right? So if you want to think back to a second and just think about in 2 dimensions, right? In 2 dimensions, we know that, if I draw 2 points, I can always make a line using 2 points. If I draw a 3rd point, most of the time that 3rd point is not going to be on the line, right? This is the same sort of analogy. So in 2 dimensions, 1 point is not enough information. 2 points is exactly enough information as long as the 2nd point isn't right on top of the 1st point, and then the line disappears. 3 points is too much information unless this point, is collinear with the other 2, which is to say that they all lie in a straight line. Or in my drawing here, vector EG is parallel to vector GF. And if that's the case, then really this is all just one line, and this 3rd point is just another point on that line already. So here's the first piece of information that is really important to grasp. If we have 3 points, we can create a plane. As long as those 3 points are not in a straight line, you have 3 points is enough information to specify the equation of a plane. Okay. Now, the other thing, that the lesson sort of makes a point about at the beginning is how you can think about, determining a plane, right? So one way is 3 non-collinear points. We've just gone over and explained that. One really interesting way is 1 point with a normal. I want you to give some thought to that, but we'll talk about it in more detail tomorrow. But this another one is worth just trying to think over. Why would you only need 1 point and a normal in order to create a plane, to fully specify a plane? As I say, let's leave that for tomorrow. What I want to focus on here is this other concept, which is part 2, which says you could also use 1 point and 2 vectors. Now, to demonstrate this, again, I want one of you hold up, 2 pencils, such that they are both, you're holding them up by the 2 ends, so that their pointy ends point away from you. So basically, in one hand, you're holding 2 pencils, you're sort of pinching the 2 erasers together, and the 2 points are headed off, the 2 points of the pencils are headed off in different directions, kind of like what this picture looks like with A and B. And it should be clear that you can basically imagine that this is the corner of a parallelogram, and that a piece of paper could be held in such a way that these 2 vectors lie on that one plane. And it doesn't matter how you hold these 2 vectors, right? The 2 vectors, no matter what orientation they have with one another, a plane could contain both of them. Okay, and let's go back here and we'll just restart this for a second and we'll demonstrate how this one would work. If I draw a vector, let's make up a random one. So V is equal to random between -5 and 5, random between -5 and 5, random between -5 and 5. And so we have this random vector 1, -2, 3. Now if I make up another vector, we'll call it U, is another vector there. Now again, there is the possibility that I randomly create 2 vectors that are collinear, which would ruin this, but you can imagine that there is a plane that would contain, these 2 vectors. Okay? Now, the reason we need a point to go with them is because we need to specify where is this plane located, right? Remember, a plane is like a line. It is a physical object that exists at certain points and doesn't exist at others. A vector is not a physical object. A vector is just a direction and a length to go. So let's make a random point. So we'll do the same thing, except we'll use a capital. It's GeoGebra. Lowercase letters it assumes are vectors. Capitals it assumes are points. So now we have a point A, and we have two random vectors, v and u. And you can see that one of the ways to construct you see the other one here, right? Point, point, point is one way to make a plane in GeoGebra. But one way is point, vector, vector. So point, vector, vector. So we're going to go, okay, A, V, and U. And that specifies a plane. It's the blue plane here we're looking at. I'm going to just disable the plane there that exists, and so we can just look at the one we're interested in. It's parallel to the two vectors I created, and it passes through point A. So a good way to think about this is, so we did sort of like a points method, a points and vectors method would be the next way. 1 point and two non-collinear vectors is perfect. It specifies a unique plane. And let's just make a note here. This plane passes through the point and is parallel to both vectors. Just draw a few more of these so you can see what I'm talking about. If I create these two new vectors, right, with point A, again, you can see that the plane is parallel to both of them and passes through point A. One last demonstration. Again, it's parallel to those two vectors and passes through point A. And that's really what this demonstrates. Okay, that you can specify a plane using two vectors and a point. Okay, so again, three vectors might not work. You can easily demonstrate this with yourself, where place two pencils, eraser to eraser, however you want on your desk, and then connect a third pencil to them with your hand. And you can easily see that, obviously your third pencil has to be eraser to eraser as well. And you can see that there's no piece of paper that's going to contain and be parallel to all three of those, unless that third vector you're creating, you're also letting it lie on the desk. And then what you've done really is you've created three vectors that are co-planar. And we'll talk a little bit about that in a minute. So 1 point and two non-collinear direction vectors works. Three non-collinear points work, and that's where we're going to sort of stop for today in terms of moving forward. We're going to, concepts-wise, you need to understand those two things. Now, the equation of a plane, okay, is all like understanding the equation of a plane is also a bit complicated in terms of just trying to figure out. Let's concentrate on the vector equation of a plane. The vector equation of a plane consists of the following objects. The plane itself, and the plane is usually referred to by pi. So I was using L and L1 for lines in 3D. Pi is usually the name of a plane, is equal to, okay, a point plus a certain direction vector. Oops, sorry, T vec M. Okay, so a certain amount of direction vector 1 plus another amount of direction vector 2. And this is the equation of a plane. And it comes from the fact of what we just talked about. A point, right? We'll just write down quickly. P is equal to a point. Let's say a point on the plane. M M is equal to a direction vector parallel to the plane, and N, or R, excuse me, what I said here, another direction vector parallel to the plane, such that, M is not equal to K R. Okay, you can't have them be collinear vectors, because then what happens is, you end up with the same problem we had before. If they're collinear, then you've underspecified the plane. There could be many planes that have a single point and a single vector, because we know a single point and a single vector make a line, and a line is like the axle of many planes, right? But two vectors that are non-collinear with a third point create a plane. This is essential information. The vector equation of a plane here, understanding this is really important. So again, what we're going to do here is we're just going to specify that T and S are parameters the same way they were last unit, just basically to say that a plane is like a line. It's a point plus a parameter times a direction vector, but then you have a second parameter and a second direction vector, okay? So T and S are both parameters, and pi is a plane that has that equation. Okay, now this, the idea behind this is also important to try to think about. What this basically says, okay, mathematically, what this actually means, what we're trying to conclude here is that you can find any other point on the plane by starting at point A and adding some amount of vector M and some amount of vector R. This is the central concept to how does the equation of a plane work. If you start at a known location, sorry, I said point A, I should change that to point P just to be consistent here. If you start at a known location and move some direction, some amount in vector M and some amount in vector R, you have to be able to get to anywhere else on that plane. Okay, any other location on the plane can be expressed using some combination of the two vectors. This is a bit of a difficult thing to understand, but I want you to try and think this over. Why are you able to move to any location on the plane using these three criteria? Okay, and I think a good demonstration of this is let's simplify a little bit from the planes in 3D for a moment and talk instead about a 2D plane. Let's talk about your desk. Okay, put two pencils on your desk, such that they are organized in a random orientation. So obviously an easy way to do this is to make them perpendicular. If they're perpendicular, then it's easy for you to see, oh yeah, I can get to anywhere on my desk by moving some amount north and south and some amount east and west, right? That would definitely get me to anywhere I need to go. So, get rid of the 3D for a sec. And then we're going to make two vectors here, I equals 1, 0, and j equals 0, 1. Now, of course, it should be obvious that anywhere on this plane, and this by plane I mean, the surface of the screen, or in your case, the surface of your desk, that any point can be located by starting at some point B and adding a certain amount of I and j, right? So for example, if I go, let's just make this a little easier for myself. We'll put these at nice snappy points. If I start at B and add 3i and then add 3j, right, I arrive at vector C. So let's just go vector B to 2, -1. So there, that u vector is 3 i's, and then this vector from 2, -1 up to point B, point C, excuse me, this vector is moving 3j. So it's clear that I can get from any point on this, from B to any point on this plane, adding some combination of I and j.